Hello students, I am Isha Mendirata. In today's video, we will be discussing types of polarization in a dielectric material, local or internal field of a dielectric material, and a very important equation which is known as clausius-mossotti equation. So let's start. We'll start with types of polarization first. There are 4 different mechanisms through which polarization can occur in a dielectric material when it is subjected to an electric field. So this depends on the type of material also. Let's see what are these 4 types of polarizations. The first one is known as electronic polarization. Then we have ionic polarization, orientational polarization, and the space charge polarization. Let's begin with electronic polarization first. That is the first mechanism of polarization we are going to discuss. Now this is a polarization which occurs due to the displacement of positively charged nucleus and negatively charged electron cloud in opposite direction within a material when the electric field is applied to it. So it's very easy to understand this statement. We know that the positive charge, that is the nucleus, actually the nucleus doesn't move because of the mass of protons, but it said that whenever an electric field is applied, the electron cloud, it will always move opposite to electric field and the positives in the direction of electric field. There's a slight displacement. So if I say that negative is moving away from the positive field, that means there is a distance being created between them. And this is nothing but dipole is induced, and I say that the material is getting polarized. Why did this happen? Because of the applied electric field. This is the meaning of electronic polarization. Let's understand with the help of a small diagram. You can see the first portion is an unpolarized atom where there is no electric field applied. But then in the right hand side you can see that electric field is applied in the right hand direction, and you can see that it's very clear from the diagram that you feel that the atom is getting stretched. Why? Because the negatives are moving opposite to electric field. So there are dipoles being induced due to the applied electric field. Let's understand more about electronic polarization. So the separation of charges induces a dipole, as I just now explained. This process is a process which will occur throughout the material uniformly, and so I say that entire material gets polarized. Then it is seen more in case of liquids and solid dielectrics. And the equation, now if the material is getting polarized, there would be net dipole moment induced, and hence there would be a term called polarisability, because we know that this dipole moment is proportional to the electric field, and we have understood a proportionality constant polarisability. So the polarisability in such type of materials is known as the electronic polarisability, denoted by alpha E. So from this equation, the equation of alpha E is 4 pi epsilon naught into r cube, where 4 pi epsilon naught are constants, and r, what is r? R is known as the radius of the atom. So I can say that the electronic polarisability is directly proportional to the cube of radius of atom. In short, I would say it is proportional to the volume, and it doesn't depend on temperature. Temperature has no effect on electronic polarization or the electronic polarisability. Now let's understand the second type of polarization, which is known as the ionic polarization. Now this is a particular type of polarization which occurs only in some particular materials which are called ionic solids. So when ionic solids are subjected to external electric field, the adjacent ions of opposite polarity, they undergo displacement, right? And there is a distance of separation created between them. This is how ionic polarization occurs. So particularly the ionic solids, when they are exposed to electric field, the displacement of positive and negative ions. What is a positive ion? From which electron has moved. What is a negative ion? In which the electron has been added. So if the positive and negative ions are separated by a distance due to the applied electric field, we say that ionic polarization has occurred. Let's see with the help of a diagram. So in the left portion, you can see that E is equals to 0, and you can see that all the ions are present in their own position. But when electric field is applied, now in this case, the electric field shown is in the left direction. So if electric field is in the left direction, the positives will move towards the left side, whereas the negative ions try to relocate towards the right hand side. So now there is a distance between the positive and negative ions, and we say that dipoles are induced. This is how ionic polarization takes place. Let's understand a bit more about ionic polarization. So it occurs only in ionic solids. Common example is NaCl, that is sodium chloride. We all know it's an ionic solid which has ionic bonds. It can never occur in covalent crystals like silicon, germanium, and the polarizability due to this polarization is known as alpha I, and this alpha I is equals to E square upon omega 0 square 1 upon m plus 1 upon capital M, where you can say why two m's are written. One is the mass of anion, one is the mass of cation. You can take small m as anion mass or cation mass, choice is yours. Omega 0 is the natural frequency, E is the charge of electron. We say that this polarizability is inversely proportional to the square of natural frequency. Now we move ahead to the third type of polarization, which is known as orientational polarization. Again, this type of polarization occurs in particular materials which are known as polar molecules, or I would say the polar dielectrics. When external electric field is applied to a pair of polar molecules, the dipoles undergo rotation so as to orient in a direction according to the applied electric field. This is how orientational polarization takes place. Now, we know that polar molecules or polar dielectrics are such materials which have permanent dipoles, which have dipoles even if there is no electric field. But the dipoles are randomly oriented. So what will happen in this case? The net dipole moment would be 0. But what happens when electric field is applied to such materials? Let's see with the help of a diagram. You can see on the left hand side that there are dipoles already even if there is no E. But on the right hand portion, you can see that an electric field E is applied towards the rightmost portion. So what is happening? The dipoles have aligned themselves according to the applied field E. That means if you compare with absence of electric field, the case absence of electric field, the net dipole moment is 0. But when the electric field is applied, you can see that the net dipole moment is not 0 because all the dipoles have oriented themselves according to the applied electric field. Clear? Let's see what else happens in orientational polarization. So as I said, it occurs only in materials which have permanent dipoles. What are such materials called which have permanent dipoles? They are called polar dielectrics or polar molecules. In the absence of electric field, actually what happens due to thermal agitation, or you can say due to the random motion of the dipoles, the net dipole moment is 0. This type of polarization is also known as the dipolar polarization, and the polarizability due to this type of polarization, it is referred as alpha O, and that is given by mu square upon 3 kBt. Mu is the net dipole moment, Kb is known as Boltzmann constant, and T is absolute temperature. You can see from this equation that alpha O is inversely proportional to T, because if temperature increases, what will happen? The dipoles would get random, and hence the dipole moment or the polarizability will decrease. So this is the only polarization which is proportional to temperature, and that too inversely proportional to temperature. Now let us move on to the fourth type of polarization, which is known as space charge polarization. When multiphase dielectrics are subjected to external electric field, especially at high temperatures, the charges get accumulated at the interface or at the electrodes due to the sudden change in conductivity, and this leads to polarization or creation of dipoles. So practically what happens, happens in this case is that between the metal plates we have kept dielectric material. Multiphase is nothing but compound dielectric materials. So at high temperatures, due to temperature also or due to the applied field also, there is a possibility that the space between the dielectric and the electrodes also gets dipoles induced, or the dipoles are induced in that particular portion also. This might be clear with the help of a diagram. So the first diagram shows the unpolarized state where there are no charges. Then you can see that between the grain boundaries also the charges have been induced. So basically, if there is a dielectric, if there are compound dielectrics at high temperatures, there is a possibility that dipoles are created at the interface also or the electrodes also. But this type of polarization is very weak and it occurs at sufficiently high temperatures. So it is almost, you can say, neglected, not taken into consideration. This occurs in compound dielectrics only. Examples are amorphous solids, like you can have carbon, diamond, etc. It takes place at high temperatures. It is also known as interfacial polarization. So what actually happens is, along with the positive and negative charges or the ionic bonds, what happens, even the free charges get affected due to this polarization. But the polarization is very weak as it is taking place at high temperatures only. Now, what we'll do is we'll discuss the total polarizability with respect to a dielectric material, which is known as alpha T. And it is a summation of alpha E plus alpha I plus alpha O. Why haven't we considered the space charge polarization? Because that is very weak, or you can say negligible as compared to these three. We already have derived the equations of, we already have discussed the equations of these three types of polarizabilities. So I have just substituted the three equations. So I have alpha T is equals to 4 pi epsilon 0 r cube plus E square upon omega 0 square 1 upon m plus 1 upon m plus mu square upon 3 kBt. Now, if I have derived the equation of polarizability, I can also write polarization, which is defined as Ne into alpha T. Now, what is alpha T? Alpha T is the above equation. So I have just multiplied the above equation by N into E. That gives me the total polarization inside a dielectric material. Let's move ahead and discuss the second topic for today, that is internal or local field. Now, what do you mean by the term internal or local field? We know that whenever electric field is applied to a dielectric, dipoles are created inside the dielectric. Or I can say there is an electric field induced inside the dielectric due to the creation of dipoles. Is that clear? Now, this is known as electric field acting on an atom of a solid or a liquid dielectric subjected to an external electric field, which is a resultant of applied field and the field due to all the surrounding dipoles. Now, there are different possibilities where dipoles are being created. So if you consider a dielectric material and just go on to the atomic level, there are different parts. Combining all of them, we say that the total internal field of dielectric is created. To find out this internal field, Lorentz proposed a method. This internal field is denoted as EINT. What he did was, he considered a small sphere inside a dielectric material, and inside that sphere he considered only one atom. And then what did he do was, he considered what is the effect of applied field on that atom. Then, now if I consider a spherical cavity inside a material, doesn't mean it will have only one atom, there will be n number of atoms. So then what did he do was, he divided the total electric field into different parts, starting from the metal plates to the surface of dielectric to the spherical cavity and then inside the spherical cavity. Let's understand with the help of a small diagram what is this Lorentz method to find the internal field. So just have a look at the diagram. So I'll start explaining from the rightmost portion, that is the field E1. What is this field E1? You can see from the diagram that E1 is due to the charges on the metal plate. So there is, you are applying electric field, that means you are applying the electric field at the metal plate. So there are charges on the metal plates, Then come towards the left portion, you have E2. Because of the external electric field, there would be charges on the internal surface of the dielectric also. Come on to the next part where there is Lorentz sphere. This is just an imaginary spherical cavity which was assumed by Lorentz. So there are charges on the sphere also. And then the last portion, that is the leftmost portion, shows you all other dipoles or all other charges inside the spherical cavity. So that means the internal field, if we are going to find out, it will be the summation of E1, E2, E3 and E4. This is how Lorentz found out the value of E internal. Let me just brief you about what are E1, E2, E3, E4. So E1 is known as the field due to the charges on the metal plates. E2 is known as the field due to the polarizing charges on the internal surface of the dielectric. So this field is also known as the depolarizing field. Then you have E3, which is due to the charges on the outer surface of the Lorentz sphere, imaginary sphere. And E4 is due to the dipoles which are lying inside the spherical cavity. Clear? Because for explanation purpose, only one atom was considered, but there are many atoms in that particular spherical cavity also. So what is the effect due to the other dipoles? So I can say that this internal field is the summation of all these E1, E2, E3 and E4, and this equation summarizing all of them is given by E internal is equals to E plus P upon 3 epsilon naught, where P is the polarization induced. So this expression is the expression for internal field of a dielectric. Let's move ahead and discuss Clausius-Mossotti equation. What is this Clausius-Mossotti equation? Clausius-Mossotti equation actually relates to quantities we'll be discussing at the end of the derivation. It's a small derivation. Now we know that polarization for a single atom can be given by P is equals to N alpha E. This is how polarization is defined. But now what do I do is, I consider total polarizability, so I have written alpha T. And we also know that what is internal field of a dielectric, so I have replaced by EINT. Clear? Now if I consider now I know that alpha T is a summation of 3 different polarizabilities: electronic, orientational and ionic. So I have alpha T is equal to alpha E plus alpha I plus alpha O. But then if I consider a cubic structure, if in a cubic structure there would not be ionic polarization and orientational polarization, because ionic polarization takes place only in case of ionic solids, and orientational takes place only in case of only in case of polar dielectrics. So I have alpha T is equals to alpha E. So I have modified my equation. Now I know the equation of EINT also. The equation of EINT is E plus P upon 3 epsilon naught. So I have substituted the same. But now I can say that there is a relation of P as P is equals to epsilon naught E into epsilon r minus 1. How did I get this equation? From the definition of susceptibility. Susceptibility chi E is equals to P upon epsilon naught into E. And I know the relation between chi E and epsilon r. It is chi E equal to epsilon r minus 1. So taking both these equations, I get this equation written in the blue colored box. Now what do? In the above equation, I have P in the LHS and RHS both. So I substitute the equation of P in both the equations and I get the equation N alpha E into bracket E plus epsilon naught E epsilon r minus 1 upon 3 epsilon 0 is equals to epsilon 0 E into epsilon r minus 1. Now what do? I just rearrange this equation and I have N alpha E is equals to 3 epsilon naught square epsilon r minus 1 upon epsilon naught into epsilon r plus 2. So epsilon naught get cancelled, one of them gets cancelled, and I am left with N alpha E is equals to epsilon r minus 1 upon epsilon r plus 2. This equation written in the pink colored box is what is known as the Clausius-Mossotti equation. This is an equation which relates microscopic quantity alpha E with macroscopic quantity epsilon r. So in today's video, we have discussed the 4 different types of polarization mechanisms We have also seen what is internal field or a local field, and we have seen the equation called clausius-mossotti equation, which relates alpha E and epsilon R. Hope you have understood all the topics I explained today very well. Thank you.